periodic trends or periodicity. I'm going to start by talking about something called effective nuclear charge, which is sometimes abbreviated as ZEF. So we're going to talk about how that can be shown on the periodic table, and then that will factor into how all of our other trends can be explained. So the periodic table has a lot of trends on it, a lot of general trends that we can kind of use to compare one atom to another. For each property, we're going to learn the definition, the group trend, and the period trend. Group trend is when you move down a group. Period trend is when you move from left to right. So if you have your trends chart and you want to write down at the top here and left to right here, that will help you, and then we don't have to write that every time. We don't have to say as you go down it increases or decreases. We're first going to talk about something called Columbic Attraction, which relates to Coulomb's law. Positive and negative charges attract each other. You know that. Opposites attract. So what two particles in our atom must attract each other? Protons, which are positive, and electrons, which are negative. So Coulomb's law, the actual formula looks like this. K is a constant that we don't need to care about. Q stands for charge. So this is the positive charge and this is the negative charge. D is distance. So what you can see is the closer the two charges are, so the distance would be smaller. If distance is smaller, then attraction goes up, right? The F stands for force of attraction. The opposite is true when it comes to the charges. The higher the charges are, the more the attraction is, okay? So the closer they are, the more the attraction is, and the bigger they are, the more the attraction is. So the smaller the distance between them, and the bigger the amount. You don't need to really worry about this formula. I just wanted to throw it in there to show you what we're actually talking about here when we talk about Coulomb's law. So the definition of effective nuclear charge is the attraction between the nucleus on the outer electrons, or the valence electrons. So if you go to your chart, whoops, you can write that in right here. And the important word is that you understand it's attraction. Okay, that's what we're talking about here. We're talking about a force of attraction. The thing that factors into there is something called electron shielding. Electron shielding is the reduction of the attraction, because we're talking about nucleus to outer electrons. That electron shielding is what we call the core electrons. And they cancel out some of that positive charge. They're blocking the attraction. Okay, so this doesn't have to do with the charge in an atom. It is related, so this isn't totally true. That has nothing to do with the charge in an atom. It's definitely related, but it's not important for you to know what that relationship is right now. So to demonstrate this process, or Coulomb's law, I like to use an example of a concert. So years ago, I went to a concert, and this is the Boston Garden, and I was all the way in the back row. So when I got to my seats, this is what my view was of the stage. So you can see this is the stage here. This is where sometimes they would come out, and I was all the way up here. I actually don't even know who this person is. This person was just a random person in front of me. So I like to call her my electron shield. She is going to be blocking my attraction to that stage. Okay, so the further away I am, the less attraction I'm going to feel to that stage, just like Coulomb's law. Because the bigger the distance, the less the attraction is. And you can think of her as your electron shield. She is blocking our view. She's blocking our attraction. The reason I like this story is because at some point during the concert, well, in between the opening acts and the actual act I was there to see, someone came and gave me and the two people I was with tickets to the second row. So I went from being up here to right here. So you can see how much greater the attraction would be if you were this close, if the distance was this short. Okay, so again, the shorter the distance, the more the attraction. The other thing that you can think about here with Coulomb's law is that you can see I was seeing a boy band. There are a bunch of them. And there was actually another boy band. Okay, so there were there's actually 5 guys there, but there's one hiding back here. There were these 5 guys, and then there was another 4 from a different boy band. So if you think about the other part, okay, even when you're all the way back here, if you have 9 people on this stage as opposed to 5 people, you can see that that attraction is going to be greater, right? Because the more protons you have or the more people you have, the more attraction you have. So no matter how distant you are, okay? So it's nice to think of that concert as your atom. The closer you are, the more attraction there is, and the more people on the stage, the more attraction there is. So as you go down a group, the effective nuclear charge decreases. Why? Because as you go down a group, you know from electron configurations, you are adding shells. Remember, those period numbers were our shells. So as you go down a group, you're adding shells. So you think about that as rows at the concert. So as you go down a group, you're getting further and further away from the stage. All of a sudden, you're in the 7th row as opposed to the 1st row, and that's going to be less attraction. So when you're adding shells, you're adding distance. More distance means less attraction. As you go from left to right across a period, the effective nuclear charge increases. Why? Because we're not changing the row there. Remember, if you're in the second period, the second energy level is the furthest energy level, right? We know that. So we're not changing the distance. Distance is staying the same. But the number of protons increases. Okay, so if you think about it as the concert, the number of people on the stage is increasing. You're going to feel more of attraction. If you go back to our Coulomb's law, this part is going up, which means F is going to get bigger. So that's really it for effective nuclear charge. Make sure you add this stuff, the increases and decreases and Y, into your chart. Okay. I'm going to add those notes to this table, this chart. But before I do that, I realized I did the opposites here. Periods are left to right, and groups are down because those are the columns. So I'll fix that before we add in our trends. So as we go from left to right, the attraction or the effective nuclear charge increases. And that is because you're adding more protons and electrons. And we're not going to increase the energy levels. So they're at the same energy level, but they're going to be bigger magnets or bigger charges. As you go down a group, the Zeph decreases because the outer electrons are further away. In our next video, we'll talk about how to fill out the rest of this chart.